By now, we should be familiar with the equation for the location of an object. For example, let's say we have a ball, and we know what the initial conditions are for that object, for the ball. We know what its initial position, velocity, and acceleration are. Then by plugging in those values into the equation, we get a picture of how the ball changes location with time. The next equation that we should be familiar with is the equation describing the velocity at a given moment in time. We have the velocity at some moment in time equals the initial velocity plus the acceleration times the time. That is the time from the initial moment until the time we're measuring at. For example, we can plug in the initial conditions also into the velocity equation. If we have the given initial conditions, then we'll have that the velocity at some moment in time is equal to 10, because the initial velocity is 10, minus 10 times t. We have for the acceleration minus 10, and then we're just measuring for some moment of time t. For example, we can plug in for this expression different values of t. That is, let's start off with t equals 0, and then we'll let the time begin running, and we'll see that not only the position changes, but the velocity changes as well. For example, when the time equals 1.48, that is after 1.48 seconds, then we can see that the velocity is equal to minus 4.83. And that's just because 10 minus 10 times 1.48 gives us minus 4.83. We also know that at that time, at 1.48 seconds, the position is 4.83, but the position is plus 4.83, whereas the velocity is minus 4.83, telling us that the object is falling down, it's moving down. We can further visualize this if we draw an arrow representing the velocity at a given moment in time. So let's set the time back equal to 0, and let's draw an orange arrow for the velocity. Note that all the orange equations and orange lines have to do with velocity, and all the black lines have to do with position. We know that at the initial moment in time, at t equals 0, the velocity is 10, because 10 minus 10 times 0 is just 10. And now, if we let the time run, then we see that the arrow becomes smaller, and then it further changes direction. One thing to keep in mind, though, is that the position and the velocities are different, and in this case, our axis, our y-axis, represents the position. That is, initially, when t equals 0, the ball is at a height of 1 meter above the ground, so it's at the one position along the y-axis. Sometimes you may see another axis, a different colored axis, to differentiate between, say, the position and the velocity. Let's run the animation again, and this time let's pay attention only to the arrow. We don't have to look at the number for the velocity right now. So if we let the animation run and the time run, then we see that the arrow becomes smaller and smaller as the ball becomes higher and higher. When the ball reaches a maximum height, we'll see that the arrow has basically disappeared, and the velocity at that moment is 0. So at the maximum height, the velocity is 0 and our arrow disappears. If we let the time continue running, then all of a sudden the arrow appears again and becomes larger and larger, but it points downwards. This tells us that the ball moves faster and faster as it falls downwards. Let's look at the animation one more time, and hopefully we can see how as the ball changes position, then the velocity changes and the arrow changes as well. Hopefully that gives you a better understanding of the position equation and the velocity equation and how they both change with time. And if that was all clear, then we can move on to the next video.